Hi everyone. This video is going to be a little bit different from my normal videos. In this video, I'm going to be asking for some help. I'm trying to understand the BPF function, bpf override return. Now in the documentation, bpf override return is a helper function that is supposed to, and I'll just read it, the documentation for you. This helper function works by setting the PC to an override function which is run in place of the original probed function. This means the probed function is not run at all. The replacement function just returns with the required value. Now, what happens here inside of the kernel is that when bpf override return runs, deep within its call stack, it runs it sets the register IP to a just return function, which is only a no-op. So what it's supposed to be doing here is replacing the probed function with a no-op. However, this doesn't seem to be my experience with how this function works. So I've created some helper programs to help me demonstrate why I'm having such a hard time understanding this helper function. The program that I've created here is called TraceX8, and it's derived from the TraceX7 program inside of the Linux samples BPF area. So what the TraceX7 program does is it sets a BPF override return to interrupt whenever a BTRFS mount is called. Because I want to kind of make things a little bit easier for myself in demonstrating my issues, I'm, instead of interrupting a BTRFS mount, I'm interrupting an x86 sys exec VE call. So let me show you. Let me run down what my code is. So the BPF code that I will be installing, all it does is it prints out some. It says that it's running a test, and it prints that out. Then it does a BPF override return, returning an EPERM onto the registers. It does an EPERM. And then if that function succeeds, if it was happy with the BPF override return, it says we're good, then it says we're done, and the function exits. If the BPF override return function misfires, if something goes wrong with it, it will say that an error has occurred. Now, the user space code which loads it uses the load BPF file function, which you can find inside of the samples BPF area. It's in the function. It's in the file called BPF load, I believe, load.c. So it's in BPF load.c. It's kernel code. I haven't messed with it or anything like that. And what it will do is it will load up this application for me. So what will happen here is if we have one more argument, so if we have an argument of 1, we will sleep for 5 seconds, which isn't very useful in and of itself. But if we have 2 more arguments, it will sleep for 5 seconds after loading up the BPF code that I've installed. And if we have 3 more arguments, it will load up the BPF code. It will then fork itself. And in the child process, we will go for a forever loop trying to run an exec on user bin ls. Every time that it fails, it will simply keep looping around. But if ls ever succeeds, then of course it will never return here. And we will finish the wait for PID because this new process, this new child process will have terminated because ls will have terminated. So first I'm going to run just with two more arguments other than the other than the argument itself for the program itself. So let me compile up I should mention that I am running all of this code on a QEMU emulated Arch install. I've got my kernel is a kernel that I've compiled myself. It's 5.6.2. And just to show you, I have got all the necessary BPF configs and error injection configs. So you can see the BPF kprobe override, the function error injection, and BPF can run itself. So I am already up and running on the QEMU system. Here's my QEMU system, and I'm just going to move that over onto another window here because I'm not actually going to use that QEMU window for this demonstration. What I have over here is I am in the samples BPF area of the Linux kernel, and I have code I have a little makefile to compile up my test application and copy it over to a directory which is sshfs onto the QEMU system. So I am actually compiling this on the same machine that I've used to compile the kernel, which is my host machine, which is running Fedora, the latest version of Fedora. I think it's 31. So I am going to compile up my TraceX application and copy it over to the QEMU virtual machine. And in this window, we've got the TraceX code now. And I am going to run it with 2 arguments. So what we will be doing is loading up the BPF code and then sleeping for 5 seconds. In this window, I'm going to try and run some applications. Now, because the BPF code that I'm installing is not discriminatory to anything, it should try and kill every execve call that is run. But let's see what happens here. It is not stopping the ls code that I'm running in this window from occurring. Now let me cat on syskernel debug tracing tracepipe so we can hopefully see these printouts to see if the probe itself is running and if it is running correctly. So let me run the TraceX 8 application again, and in this window I will again, I'm able to run my ls command. We can see that the printfs for the happy day scenario are occurring. So we see that the test is running, and we see that the bpf override return function is returning 0, which is a measure of success. So the probe is running, bpf override return is running, and in fact this print here is something that I've instrumented the kernel with to show that this is the IP, the reg pointer to IP. The reg pointer to IP is changing from now that will point to the x86 64 x64 sys execve call. And this is the just return function inside of the kernel. So it is setting the IP to it is doing the things it's supposed to be doing inside of the probe. It's just that the probe is having no effect. The bpf override return function is having no effect on the actual running of my ls command here. Now I'm going to now set I'm now going to use 3 parameters, which will mean that I will run a fork and I will loop over this little code trying to do user bin ls from within the child process to the process which loads the BPF code. So as you can see here, we are successful in stopping the ls command from running, but not permanently. So what we should see here, because this is a forever while, we should continue to loop forever like this, saying doing exec, the return is an error. Doing exec, the return is an error. We should never actually successfully complete this exec VE. At least that's my understanding from the documentation that I see here in the kernel of the UAPI Linux BPF.h documentation. Now another problem is it doesn't seem to be entirely deterministic about how many times we will fail this exec VE. So let me change this code here so that I don't actually run the sleep call, and that so I changed the code so that I'm not actually running the sleep code, just so that I can demonstrate this a little bit faster. So I'm going to run the same code again. We're going to be going through this area over and over again until exec VE successfully completes. Well, that time it was on 132 tries, 131 tries before it failed. So on the 132nd try, exec VE passed. Let's do it again. That time it was 798. This time it was 82. This time 139, 26, 330. So you can understand my confusion about what this BPF override return function is supposed to do. Now, I've also got another sample program here. This program, which I called x.cpp, uses the C++ BPF helper functions in the IOVisor GitHub repository. This function is similar in that it does a while loop trying ls, but this function is actually a little bit more intelligent in that, well, actually it's not more intelligent, but what it's trying to do is it's trying to kill applications. It's trying to kill applications itself, similar to the TraceX user code. Now, in this function, the difference is that I am running the loop to try and do the exec VE call from within the parent after the fork occurs. So I have kept this code here, and I'm going to make the application. And I am going to run the application. So you can see that we failed 3 times before the ls actually ran. Let's do it again. And it was 1, 2, 3, 4, 5 times here. And it was 6 times that time. So I'm going to change this up so that instead of doing the exec VE call inside of the parent process, I'm going to do it in the child process. Now this time, it's always working. And as we saw in the TraceX user, it was the child process which was doing the exec VE. So this isn't an issue of child versus parent. This is some other issue that I'm not quite understanding. So let's set it back to being the parent which runs the exec VE and run it again. So it did it quite a few times before the ls was successfully run. But now let's add this sleep in right before we start doing the while loop for the exec VE. And you can see now I'm successful in this parent process. So I think that this BPF override return function, the BPF override return function, has some sort of timing going on with it. So my first theory is that BPF override return only works on the process which loads the BPF code or its children, and it has some sort of timing associated with it, so that, well, I don't know why it would have any timing associated with it, but it seems, from my experimental data here, it seems to have some sort of timing stuff on it. And again, like, I don't understand what's going on here, and what I'm looking for is an expert to help me understand what's going on with BPF override return. So thank you very much for watching. I'm sorry that I wasn't able to help anyone learn some things about Linux or with BPF code or with BPF override, but I hope we can get one of the experts on BPF in the kernel to respond to this video and hopefully educate the rest of us on how this BPF override return helper function is supposed to work. Thank you very much.